Good morning, mathematicians. We're back. I survived the mountain. Yeah. Wait, am I streaming? Yeah, I'm streaming. We're just being really laggy today. Yeah. What to talk about? I don't know. I guess Langlands parameter stuff again. I think last time we ended up on the point that we had come full circle. Whoa. Never mind. This title caught my eye. Just discovered an academic from outside. Ooh. That's brutal. Hello, Edit Smith. I mean, I don't know. I mean, it seems to me like I think this person could still publish, right? If they're in year 3, and the other like shitty rushed paper is already out. I don't see why this person couldn't still publish their main thing. Especially, I think, in the modern era. It's easier to communicate online what happened. Don't want to continue within academia. Well, okay. Yeah, I don't know. Well, definitely name this person. 100%. Don't be shy. This person's a dingus, so call them out. What advice the supervisor give you? Yeah, what advice did the supervisor give them? Wait. The best way forward is to move on and see what we can put into your thesis. Yeah, I mean, still just publish everything. I don't know what to say. Yeah. Well, so many people have commented already. Okay, let's talk about math. So where were we before? I think this was the big punchline, right? Langlands parameters are in bijection with orbits. So, how do we beef this up? Well, in order to get the I think I also mentioned too that there could be more than one representation going to a Langlands parameter, a given Langlands parameter, but there'll only ever be finitely many. And how should you parameterize those representations which go to a given Langlands parameter? Well, those should be parameterized by certain kinds of local systems on the orbit, H equivariant to local systems. So, what should those be? Well, so we kind of came full circle because I had you consider this Langlands parameter and this infinitesimal parameter for which we saw the Q eigenspace of this thing broke up into our previous stratification, right? So then the question is, well, what are the representations? What are the representations? Oh, and I guess the case I started with, though, I guess I did a fancier case before, where we had two local systems on this orbit. I'll talk about when that comes up, but the case we investigated was when this was the group, and so we just had no local systems on either of these orbits. So what are the representations that this goes to? Well, this is something we've also seen before. On, I don't know, 3 months ago or so, I made a whole bunch of streams about the representation theory of GLN. And this is, well, exactly where that theory intersects. So let me see if I can find a different way to say it. Yeah, I don't know. I guess I'll just have to remind you. The yeah. So I talked about this theory of multi-segments, right? Where all of the representations up to some details I was sweeping under the rug of GLN, at least those principal block representations, could all be written as some parameterization QA, where A is what we called multi-segment, which means it's a multi-set of segments where each segment is an ordered set of complex numbers, but each differing from the next by adding 1. Right? And so here's basically how it goes. Here's how the construction should go. Given one of these representations labeled by this multi-collection of integers, the infinitesimal parameter is going to be given by, well, you simply take all of these, and you just take the omegas to those powers. So this would be omega A1, direct sum. So this would be like going down the diagonal of the matrix. Omega A2, or sorry, A1 plus 1 plus ... plus omega B1 plus omega B1 plus 1 plus ... until we get all the way down to omega BR. Okay, so that is going to be the infinitesimal parameter. And then I claim that if you take the following matrix, so if you let n be the length, so the number of elements in this segment, so that will always be bi minus ai plus 1, and then you let maybe I could call it j and I to be the ni by ni Jordan block. So that means you have 1s on the off diagonal. And then you let x be the, I mean, I'm writing direct sum, but I just mean you put these blocks on the diagonal. Then I make the claim that this x is in the Q eigenspace, of conjugation by this lambda. And therefore, this pair, lambda x, determines for us Langlands parameter, SL2C, a Langlands parameter of GLN for some appropriately chosen n. Well, this n will be the sum of this n will be the sum of the lengths of each of the segments, which is also the same n for which this representation, the n, it's a representation of a group of. Well, it's kind of weird. Only one person's commented so far. Normally, 9 o'clock on a Saturday. This is like busiest office hours. So, where are we here? Yeah, finally. Yeah, I guess that was the point. So, if we unpack, if we sort of go backwards, we go the other way. We take our example from up above here. Well, then all of the possible segments. So if I look at this, right, and I think about, what are the segments that representations are built out of? Well, I've got the numbers 1/2 and -1/2. So I need to think about all possible multi-segments I could build with those two numbers. Well, of course, I could have the multi-segment that contains the single segment with these two elements, or I could have the multi-segment that has each of these two singleton segments, and those are the only possibilities. So clearly, those are in bijection with the orbits, and so we can see. I mean, this corresponds, of course. The like this Jordan block of size 2, right? So by the formula I gave, this should correspond to the Jordan block of size 2, which of course corresponds to this orbit. And I mean, here the Jordan blocks of size 1 are both just the zero matrix. So you put those on the diagonal, and in fact, you get the zero matrix. Okay, great. So we see the correspondence. So so we have these. We know now, in terms of the variety we wrote down, we know what the corresponding representations are. And yeah, how are these representations built? Where do they come from? I am good, Argya. I am good. Thanks for asking. How are you? I should put these in a different order. Well, both of them can actually be seen as being built in the same way, although it doesn't really highlight the usual way we carry out the process. But I guess I can just write down one sequence that encapsulates them all. So these, we have our norm character, and these numbers tell us what power to put the norm character to. So if I take the norm character and I take the external tensor product of the norm character on both factors, so on my torus in GL2, and I induce this to the whole group through parabolic induction, then this representation ends up being, I get a copy of the trivial representation, which sits in here as a sub-representation, and the quotient is an infinite dimensional irreducible representation called the Steinberg representation, which is the other one. So, which we've talked about before. So in fact, actually, you can essentially see from the multi-segment theory and this recipe that I've cooked up here that in general for GLN, if you take this representation and you induce the character, maybe not to confuse it with the A's and B's above, I'll write it this way, say Z1 up to Z V to the Z R, we'll call it, then the isomorphism classes of this representation are in bijection with the orbits in V lambda for lambda given by omega to the Z1 O plus dot 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 O plus omega to the ZR. Of course, this doesn't tell us the multiplicities, so it could be the case that some representation appears more than once in this induced representation. But up to distinct isomorphism classes of the irreducibles that do show up in there, those are distinct up to bijection. Okay, so what about the other kinds of representations, though? Because so far, what I've told you basically just sets up a bijection between those representations, QA, where A is just a multi-segment determined by complex numbers, and those biject over to those infinitesimal parameters that are just, direct sums of these norm characters to complex numbers. So essentially, these are just ones that are built out of direct sums of irreducible one-dimensional representations of the Veidalin group. So we're not seeing any higher dimensional irreducibles showing up in here, right? So the question is how, where do the two-dimensional, like if I had, if I have this quotient to some Galois group, and let's say that Galois group was S3, and I have, a two-dimensional irreducible representation of S3, what irreducible representation of GL2 does that correspond to? Because that's not captured by the process that I said above. Well, one of the so clearly there's something important going on with induction, right? The sort of way that we construct these kinds of representations, which I've covered in more detail in the past, has something to do with this process of parabolic induction. And if you know anything about finite groups and representation theory of finite groups, you know that induction, there's induction, say if H is a subgroup of G, we have induction and restriction. And these give us a pair of adjoint functors, right? So I induce and I can restrict. So a representation for GLN, but for GLN we use a special kind of induction, and maybe I'll call restriction J for reasons. Well, there's two reasons. I mean, I and J go together, but then also J for the Jacquet functor, as it's called. So again, just like how parabolic induction for GLN, for example, is a spicier, fancier version of induction, probably the adjoint functor we're going to make for it should also be somewhat fancier, the Jacquet functor. So how do we do that? Well, actually, I'm not going to define it for you, but the vibes are just the same as restriction. The vibes are just the same as restriction, essentially. You just need to do a little bit more fancier things to make sure stuff works out, but you can think of it as just restricting representations down to some subgroup. Again, we're going to focus on Levy subgroups in particular, and there's some accounting of like a parabolic you have to do. But the point is, so far the representations we've looked at can somehow be probed by induction, right? They seem to appear as subs or quotients, right? And I forget which way I always confuse myself about which way the adjunction goes. No matter how many times I've used the adjunction to prove things, I just always forget which one's on the left and which is on the right. I think Jacquet is on the left. It doesn't matter, right? So but the thing is, suppose let's say it goes this way, right? Suppose I have some representation pi, and I want to see if somehow I'm trying to construct all of my irreducible representations, and I want to, gosh, how do I say this? I want to see which of those representations can I construct by induction, by which I mean, let's say I've fully understood the representation theory of my two-dimensional torus, right? And I'm trying to construct all of the representations of GL2. So I might hope that it's the case that as I run over all of the irreducible representations, tau of my torus, maybe if that varies over the whole set of irreducible representations of the torus, and I induce all of those, maybe all of the irreps of GL2 will show up in here, right? In one of these. And so it turns out the answer is no. This does not happen in general. If you just run over all the irreducible representations of the torus and induce, you miss a whole bunch of representations. So there's two ways to phrase this. So a representation is, we might say supercuspidal, or, okay, you could just say cuspidal even. It's cuspidal if, so we would say pi is cuspidal if there's no representation sigma for which this is not equal to 0, right? So in other words, if it is equal to 0 as you run over all sigma, or equivalently, if this representation, what am I trying to say? Yeah, pi is cuspidal. Yeah, if it can't be probed by any sigma. Or conversely, if, or not conversely, but equivalently, if this is 0 as you run over all sigma. Well, the only way that could possibly be true, right? Because every representation has to have a 0 representation. So the only way that could be true, another way to say this, is if the Jacquet down to every possible choice of Levy subgroup, if this is 0, then we would also say that pi is cuspidal. I mean, different authors have different conventions, but then supercuspidal usually means irreducible plus cuspidal. Okay, so finally, the Langlands correspondence then predicts a couple things. So first, we say that the supracuspidals, these are the things that correspond to the representations of just the V group of Galois type. So those you could take the like SL2 factor to be trivial, and these factor onto, these are pulled back from some Galois representation. Supracuspidal and cuspidal are the same in characteristic 0, but different in positive characteristic? I don't think that's different authors have different conventions. So I've seen people say cuspidal just means that the Jacquet is 0 for all levies, which is definitely not right. So there's no implication of irreducibility there. And then they say the word supracuspidal to mean specifically an irreducible cuspidal representation. So definitely those are not equivalent concepts, right? Because if you have two irreducible cuspidal representations, right, meaning that their Jacquet modules are trivial to all levies, if you take the direct sum, it will also be true. So that will still be cuspidal in that sense. However, I've also seen some authors just reserve the word cuspidal specifically to mean irreducible cuspidal. So yeah, you have to be careful. It depends on who you're reading, because yeah, the depending on your source, supracuspidal and cuspidal definitely don't mean the same thing, or they do by definition, depending on what paper you're reading. Yeah, I don't know much about the positive characteristic stuff or what the terminology is there. So I don't know. Maybe the super adjective, or super prefix, I should say, is means something else in positive characteristic. I don't know. No, but I think even I don't know. I don't know so much about the positive characteristic case. But yeah, so the point is supracuspidal representations. These correspond to those will correspond to the things of Galois type. So in particular, this should say that supracuspidal representations of GL1 should be in bijection with those representations which are just characters of Galois groups. And again, this is basically just local class field theory again, because GL1. So maybe I'll just remind you, the Levy subgroups of GLN are just they don't have to be this on the nose, but up to conjugation, they're just blocks of smaller GLNs along the diagonal. So GL1 doesn't have any Levy subgroups, so vacuously everything is a cuspidal representation. So all of the irreducible representations are supracuspidal, and so those should be in bijection with this. Yeah. Then, more generally, I guess in order to articulate the next step of this, I need to go back and be more honest about what's happening with the multi-segment theory. So maybe I'll leave that for next time. I think I'm gonna get going with my day, and by that I mean do a whole bunch of marking. So yeah, that's that. I'll see y'all soon.